Okay, so this morning I'm going to discuss how to do mole problems. So if you watched the lecture on the very last slide, there was a bunch of problems which I didn't go over then, so I'm going to go over those now. And I'm also going to describe briefly the lab, which is on stoichiometry, and which is going to be the topic of next week's lecture. So I'm going to give you a little more time to do it, but I just thought I'd show it to you today in case you want to get a start on it. All right, so let's go ahead and show you my screen. It's impossible to find the right page. I think that's it. Okay, so this is, again, these are the ones that are on the last page of the slide, but I just copied them into this format so that I can write on the screen here. And these are also in the handout associated with the lecture. So if you want to print that out, you should be able to, and the answers are at the bottom, but of course I'm also going to give the answers here. Okay, so let's get started on these. So the first one is, and these are all very similar to the homework problems. So hopefully if you can do these, you can do the homework as well. So the first question asks, it says you need 0.5 moles of calcium carbonate for a chemistry experiment. Calculate the mass in grams. So to calculate the mass, first of all, we need the formula mass. So that's going to be, that's right here. And then I'm not going to go back and forth the periodic table, but hopefully you have it in front of you. But calcium is a mass of 40 grams per mole, and there's one of them. And then carbon is 12 grams per mole, and there's one of them. And then oxygen is 16, and there's 3 of them. And then I'll put in parentheses, that's in grams per mole, so I know what my units are. And then when we add that all together, this is 100 grams. So now we know that we have 100 grams of calcium carbonate if we have 1 mole, but we don't have 1 mole, we have half a mole. So what we're going to do is write down 100 grams per mole, and then multiply by 0.5 moles. The units cancel, and then we end up with 50 grams. So that is how much calcium carbonate we need. And this is very useful because if we did need 0.5 moles of calcium carbonate, which we might need if we know we need that to react with a certain amount of something else, it's hard to know how to get that much unless we switch it to grams. Now we can easily weigh it out on a balance and get exactly 50 grams, which is what we need. Another thing I want to mention here, and I'll emphasize it as I continue, is that make sure you always show your units when you do these. If you see here, moles canceled, and I always write this down because even if you've been doing these for years, it's very easy if you don't write down the units to write it the wrong way to divide when you're supposed to multiply. If I show my units and they cancel and I end up with the units that I want, which is grams in this case, then I know that I've set it up correctly. So let's go to the next one. What is the mass percent composition of sodium in sodium phosphate? And then it asks for the mass percent composition of phosphate. So again, when we have a problem like this, the first thing we're going to need to do is figure out the formula mass, which I'll just abbreviate FM. And for sodium, it's 23 grams per mole. And in this case, we have 3 of them. And then we've got phosphate, or phosphorus, which is 31. And then we have oxygen, which is 16, and there's 4 of them. So when we calculate this out, we end up with 164 grams per mole. So I did the arithmetic before I started so that I can do these a little bit more quickly, but I would recommend that you practice yourself so that you get used to entering these into your calculator and end up with the same answer, because if you enter it in wrong, and you might think that you're, you know, doing the calculations in the correct order and you're not, and end up with the wrong answer. So it can be a little bit, even though calculators are really powerful, it's also, there can be mistakes because of the way you enter the numbers, particularly when you're dealing with scientific notation, which we will be in a couple of problems here. Okay, so now we've got our formula mass. Now I'm going to go back and read the question again, because usually by the time I get to this point, I've forgotten what I'm supposed to do. What is the mass percent composition of sodium? So in this case, what we need to do is the mass percent composition means we need to know the mass essentially of sodium and compare that to the mass of the total thing. So basically in this case, sodium, there's 3 of them. So it has 23 times 3, that is basically 69. And we can, again, write our units here, but they are going to cancel in this case. So we've got 69 grams per mole divided by 164 grams per mole, which is the total mass of this whole thing. So that's basically, this is the amount of mass that is due to sodium. This is the total mass. And then when we divide, we get a ratio of 0.42. Again, there's no units because they cancel, but that's good because what we want is a percent. And so what we do is then we multiply by 100 and we get 42%. So this is 42% sodium. And then to get the mass percent composition of phosphate. So again, you've got to really watch the wording here. And this is a tricky one because phosphorus, and let's see if I'm spelling it right. Okay, phosphorus is the element P. Phosphate is one of those polyatomic ions, PO4. And I know they look similar, and they look similar because there's a P in phosphate. But be really careful about these. And if you're not sure, look at the periodic table, then also in the table of your polyatomic ions to make sure that you know which one you're dealing with. So in this case, it wants phosphate, which is this. So basically, since sodium is one part, the other part is phosphate. So basically what we can do is we can just subtract. So 100% is the total because there's 2 things here. If there was 3 different components, we'd have to, we couldn't do it this way, but there's just 2 different components. So 100% is the total, and we get 58% PO4, phosphate, or yeah, phosphate. And then you can also do this. So that's one way to do it. We could also just calculate it out the same way we calculated the sodium. So that would be 96. So basically this whole thing is the mass of phosphate, which is PO4. So that's 96. And then we divide by 164. And I'm not going to put my units here because it is a ratio, although I probably should, but I'm running out of room. And we would end up 58%. So we end up with the same answer either way. But when you have the opportunity to do something 2 different ways, I recommend that you do it. Number 1, it is more practice. And then number 2, you can check your work. If you come up with a different answer, it means you made a mistake somewhere, and when you have the 2 answers agree, then you know that there's very little chance you did it wrong if you do it by 2 completely different ways and get the same answer. So I'm going to clear those so I can start scrolling up. Okay. So the next question says 0.6 moles of sodium phosphate. So it's the same compound is above, dissolves completely in water and forms Na plus and PO4 ions. So this is many polyatomic ion compounds, and in fact, many ionic compounds can dissolve in water. Not all of them. Some of them are actually insoluble. So we'll learn a little bit more about next week. But this one is soluble in water, so it can separate into 2 different ions. So how many sodium ions are formed? All right, so, and for this one, I gotta go back to my drawing tool here. With moles, mole problems can be, the tricky part about them is the mole is so powerful. There's so many different kinds of calculations you can do with it. And that can make it, I think, harder because it's not like you're always doing the same thing. So in this case, again, we can convert from moles to grams, but we can also convert from moles to particles, and that's what we're doing here. So this is a different, kind of going a different direction. So we've got 6 moles, and then instead of the formula mass, what we need is Avogadro's number, which is 6.02 times 10 to the 23rd, and then it's particles, like any kind of particle. So in this case, we want ions. So this is ions, and that's per mole. So in 1 mole, there's 6.02 times 10 to the 23rd ions. So like when you see that you want some kind of particle, whether it's ions or atoms or molecules, this is what you use, Avogadro's number. If it's asking for grams, you need the formula mass or the atomic mass or the mass of whatever you're dealing with. So just like make sure you look at the question first and see what it's asking for. And sometimes we convert all the way from grams to molecules and the reverse, in which case you need both bits of information, and we'll do that in a couple minutes too. So again, this is Avogadro's number. It's got lots of significant figures. I often just use 6.02. Since this is 0.6 moles without, I could probably just use 6, but I'll add that 0.02. I'm not too concerned about whether you have the right sig figs for this. It's hard enough to do these anyway, so we won't worry about it. So anyway, again, I'm going to make sure my units cancel, because in some cases you need to divide, sometimes you need to multiply. You can use, on the lecture I showed like a little one of those things where you can kind of try to like remember how to mnemonic device, that's it, how to do it. But for me, my favorite thing is to always write my units and then make sure that I cancel. The units I don't want cancel, and the units I do want are still there. So we end up with ions. So that looks right. And then, so we end up here with 3.6 times 10 to the 23rd. Now, if we look at this, so that's, I multiplied by 0.6 moles, but if we look again at the question, it says how many moles of sodium ions are formed. It does not ask, or how many sodium ions are formed. It does not ask how many of the sodium phosphate formula units there are. It asks for sodium, and notice that there's 3 of them in each sodium phosphate. So essentially, 3 sodium atoms are going to be released each time one of these units dissolves. So we have to multiply this times 3. So that's, the answer is about 1.1 times 10 to the 24. And again, I could probably just say 1 times 10 to the 24 because I only have 1 sig here, but this is when I calculated it out to more sig figs, that's what I get. So that is the answer for that one. And then again, since these are complicated, I could have multiplied 3 out here. You can do it here. It doesn't really matter where you do it. You're going to end up with the same answer. But just make sure you keep looking back at the problem and make sure that you're answering the question that's asked, because there's a lot of different things I could figure out related to moles, and so you got to make sure you're answering the question.